on recursion too. The first couple slides may seem like review, and then we'll kind of get into the meat of the concepts here. Okay, so here, if we take a look at this function, hopefully this looks pretty familiar, right? It's a function in which all we're doing is we're passing in an array into logs and array. Oh, you guys don't see my screen. None of you guys see my screen. Oh, this is such a bad day for technology. Okay, do you all see my screen now? Yes. Perfect. Okay, cool. Yeah, so let me just move this to the bottom. Okay. Yeah. So here we have a simple example of a logs and array function, and conceptually it looks very straightforward, right? I pass in an array into the function, and all it does is it goes through the length of the array, and then the console logs out the element or the element at each index. Now, if I was to have you console log out every element in this logs and array function on line 8 there, right? Notice what I'm passing in. I'm not passing in an array with 3 numbers. I'm passing in an array with 2 elements. The first element is a 1, which is a single number, but the second element is another array. And we've seen this kind of nested array setup before, right? And if we think, okay, if I have an array and I want to print out every number in the array, well, I already have a function that kind of does that, right, on line 1. And so where we're getting at with this particular example is we want you to see that really, like, fundamentally the power of recursion is not that we're trying to solve every problem kind of in one go, but really we break down a more complex problem into a bunch of smaller mini simple problems, and we solve those mini simple problems over and over and over again. So in this case, for logs, if I wanted to write a function that could take in an array, and within the array, I will have either nested arrays or numbers. And if I want to print out every single element, no matter how deep the nesting is, well, the bigger problem is I need to print out this complicated array. But the smaller problem that I'm actually really trying to solve here is just to say, great, I just need to give you an array, and I just need you to be able to print out every single thing in that array, right? That becomes kind of like the mini problem, or that becomes like the core problem that we're trying to get at here. And so if for example, on line 8 there, if I want to write a function that is able to take in the nested array that we see there and have it print out 1 and then 2 and then 3, that requires us to actually go through the inner array, grab that element, which is the array of 2, 3, and print out every single element in that array, right? And at every juncture, all we're really trying to do here is take in an array and print out everything inside of it. And if one of the things inside of it is another array, well, all we have to do is take that array, pass it into the function again, and then have that function print out every single thing in that array. And the power of recursion, as we saw yesterday, is we're actually able to do that in almost an indefinite amount of times, right? We don't. The real power here is that we don't need to tell it how many times to do it. We just say, hey, keep doing it until we hit our base case. If you remember that term from yesterday, right? Until we hit our base case, until we hit the situation in which we should be stopping. And so if we want to take a look at how we should approach this problem then, right? Before, we still want to have our function that is able to handle an array, right? We still go through every single element in the array, but now we actually have an extra kind of caveat here. And the caveat here is we actually need to check each element. And more importantly, we need to check to see if that element is an array or not. Okay, if it's not an array, so I'm skipping to lines 8 through 10 first, you'll see that all we do is we console log out the element, same as the example we saw on the last slide, right? We just say, great, if you're not an array, I'm going to assume you're a number. I'm just going to print you out. But if you are an element, so if the if clause on line 5 returns true, then we go to line 6, and all line 6 does is we recursively call the function, right? We call logs and array again, except now, rather than passing in the entire array, all we're passing in is that element. And that element is an array, because on line 5, we did a check to make sure that the element is an array before we passed in that element into the logs and array function. And when we do that, what happens inside the inner logs and array is that's going to print out. So let's walk through this example together, right? So right there on line 14, we see us passing in the nested array 1, comma array 2, comma 3 into the logs and array function. And if I look in my call stack, well, at the first step, all I do is that's where I start off at. And as it goes through, the first element it checks is just the number 1. And it says, oh, great, is on line 5, is element, right, is 1 an array? And the answer is no, it's not, it's false. So we jump to line 8, which is the else clause, right? And on line 9, all we do is we console log out that element, or we console log out that 1. Okay, and that's where the 1 comes from on the top right hand corner of the screen. The next element that we checked in is going to be the array 2, 3, and we say, great, if that element is an array, which it is, well, on line 6, let's call logs an array and let's pass in this inner array of 2, 3. And so that's what we see kind of build up on our call stack, right? Remember, a call stack always solves the problem at the very top first. Just like how at a buffet, if you have a stack of plates, you'll probably take the plate at the very top of the stack first. So now if I look at my call stack, now I see that my computer is prioritizing solving this logs an array with the array 2, 3 before it solves the previous problem, right? And the answer for and the reason for that is just because, hey, logs an array 1, 2, 3 cannot be solved until I solve logs an array 2, 3. And so if I look into how logs an array with the array 2, 3 works, and I'm going to print out the 2, which is the first element because that element is not an array, and the second element, which is also not an array, which is 3. And now I finished processing that function. I can take it off my call stack, and then I go back to the previous call stack or the previous task on my call stack, and I pick up where I left off. And where I left off was at the end of the array. So now I'm actually done with the function. Does that make sense to everyone, what we just did?
So David, the 1 that gets returned first,
Yep.
does that actually get returned first, or does it sit down there until it goes through everything and it just kind of has it stored?
So it doesn't get returned, it gets console logged. And so console log just happens kind of like synchronously, or it happens in a very linear process. And so, so if I go back to this example here, as I hit the first element, it just prints it out, right? Nothing is quote unquote being stored. Like right now, JavaScript is just doing it as it goes. And so right now, it already prints out the 1 to my screen, and then it processes the second element of 2, 3.
Okay, but if line 9 was a return element, when does that get processed?
If line 9 was a return element, then as soon as we hit line 9, our function's done, right? Because return exits out of our function. And so our logs and array function would just process a 1, it will return it, and then the entire function would just terminate then and there. So we would actually never make it to our second element.
Okay. Oh, okay.
Right? Because remember, return exits a function. Cool. Any other questions?
Is it common practice, what is it common practice to create a function without any return statement?
It depends on what you're trying to do, right? Return statements. So let me give you an example, right? If I have a function that, let's say I wanted to draft an email for me, right? Like if I say, hey, if I give you a person's name, can you give me back, an email with their name kind of embedded in it? In that case, I really care about the return value, right? Because I'm going to take whatever the function returns and I'm going to use it somewhere else. Okay. On the other hand, if I have a function that sends an email for me, well, I actually don't care what that function returns, right? I just need to actually do that thing. And so it's less of a normalcy thing and more like, okay, what's the purpose of this function, right? Do you want it to return something because you're going to take that back and use it? Or do you want it to just do something? Now, in most cases, even in the latter example where all you want is a function to do something, usually those functions will also have a return statement, and that return statement will most likely be some sort of status update to say, hey, success, right? Or, oh no, failure, for whatever reason. So your intuition is correct in that in most cases you will have a return statement, but like fundamentally speaking, it's really kind of what are you trying to do. And if you needed to give you back something, then yes, you want a return statement. If you don't, then you just don't care, right? This is like the difference between like the for each array function that we talked about actually at this point more than a week ago, really. Because what for each does is for each says, hey, I'm going to assume you don't care what I return, and all you care about is just for me to do this function, right? If you do care about what I return, you want to use a different function. And so it's less like what's correct and more just what's your purpose here. Does that make sense?
Yes, and to just satisfy my need for return statements, could we technically add a return statement on this example and just like between line 11 before line 12, or just return
You
colon?
you could. You could. In this case, it wouldn't do anything. Right. Yeah, it wouldn't do anything because we would just print everything out and then we would return nothing at the end or return undefined, which we were going to do
No,
anyway.
yeah. The return undefined would definitely jump out of the function. That, yeah, you're right. Okay, thank you.
Yep. Cool. Any other questions? Awesome. So let's click through this. Okay, cool. And so one last thing I'll mention here, and the reason why I'm saying this is a bit different than problems we saw yesterday is what we've done here actually with this recursive function is you know how yesterday we kind of had the option to say, well, if I know that this is going to be done X number of times. Well, here even if no matter how nested the array is, right? Even if I have no idea how many layers of nesting there is, if there's 5 layers, if there's 20 layers, if there's like 150 layers, it doesn't actually matter, right? Because the way that my recursive function is set up is to say, hey, if something on line 5, right? If the element is an array, go to line 6, logs an array, and just keep doing that over and over and over again until at some point where we are going to go through every element in the array and finish everything, right? And so the real power of this recursive function is before I start, I don't need to tell it how many times to do it, right? I can just say, hey, start doing this, and at some point, I'm going to assume you finish. Okay, and so this is one example of the kind of problems that you cannot do with a for loop, right? Because a for loop, I mean, I'm sure there's some way to kind of over-engineer a solution with a for loop if you really wanted to, but typically speaking, a for loop you kind of need to know in advance how many times you want to do something, or at least have some sort of determinant. Here we don't need to tell it, even though we have a for loop theoretically speaking on line 2 there. Like the way the function itself operates is like, hey, if one of the elements is an array, call yourself. If one of the elements is an array, call yourself, right? And so there's no limit to how many times we're telling this function to do something, and so therefore this function handles kind of like indeterminate data or like uncertain data a lot better than the traditional for loop. So if we look at another example that's almost identical to the previous one, except now we will have this, we will make use of the return statement here. On line one we have this function called concat else. Once again, we pass in an array, and just describing what this function is supposed to do is it's supposed to take in an array of letters and join all of the characters in together. And for now, let's just assume that the dot join function does not exist. We could really easily write a for loop that goes through every single element. We start with an empty string, and we just keep adding elements to this final string on line 4 and 5. And then when we're done with the for loop on line 7, we return the final string, right? This just joins all the letters together into a single string. But on the other hand, what if now I'm saying, hey, what if the data that I pass in could either be an array of characters, or there could be nested layers of arrays of characters in there as well. And so once again, right, if you look at the layout of our problem, it actually looks very identical to our previous example. The two main differences here are, one is on line 2, we now create this final string, and then on line 11, notice how we also return the final string, right? So now all we're saying is, what mini problem is this function solving? It's saying if I give you an array of letters, join them together, right? Edit this final string, which starts off empty, edit it, add stuff to it, and then give it back to me, right? And so in this case, I do care about what the return statement is, because I plan on taking what is being used here, and then, I plan on taking what is being returned here and using it somewhere else, okay? If we dive into the guts of the function itself, on line 3, we have our for loop, which all we're doing is still iterating through the array. Line 4, we extract the element. On line 5, we check to see if the element is an array. And this is very crucial, and I think this is the part that most folks mess up when they first start looking at this type of recursion problems. Notice how on the right-hand side of line 6, we are calling concat else, and we're passing an element, right? So we are recursively calling ourselves, right? We're saying, hey, if the element is an array based on line 5, call concat else, recursively call yourself. But now, in the last example, all we did was print out a number, right? Console log. there was no sense of continuity. We didn't take what was being returned and using it. Here, we actually do care about what's being returned, right? And really what we're trying to get at here is to say, hey, whatever the recursive call returns, I need to add that to my final string. And so if we take a look at the call stack again to see how this works, in practice, once again, in the very base of our call stack, we pass in a nested array, and the final string for that iteration of it is so far is going to be blank. As we process the first letter, we then go to line 7, which is to say that the element is not an array. We go to line 8, which adds the element to the array, right? So we add the string e to the character a to the final string variable, and then we hit up on our second element, and our second element basically says, okay, let's go to element 2 or index 1 or element 2. Is the element an array? And the answer is yes, it is, because it's the array b comma c. And now we're on line 6, and line 6 says, hey, let's recursively call ourselves, and let's add that to final string. And so I can't stress enough how important that return is, right? Because now we care about what concat else returns. Concat else in this point is returning a string, and we need to know what that is because we need to add it to our current string, right? We need to add it to A so we can keep track of all of the letters that we've seen so far. And so if we look at our call stack, basically because I called concat else with the array b comma c, this requires us to now add that function call concat else the array b comma c to our call stack. And so let's start there now. Okay, in that iteration of the array b comma c, our final string variable initially is blank, and then as we go through every element in the array, we add a b, and then we add a c. Okay, right now, because both of these elements are just simple strings, my if clause never gets triggered, right? I go to the else clause in both instances, and then I add b, I add c, and now my string is just b comma c, or sorry, it's just bc. And then, really important, right? I don't just get the string bc and say, great, I'm done. On line 11, I return the string bc to whoever called me. And where am I being called? If I look on the bottom right corner of my screen, I see concat else is being called there. So let me replace that with the string bc. And I can't forget to add that back to the string a, right? To finish up where I left off in my previous function. And so now that string becomes a, b, and c. Sorry, it becomes a, b, c. And then I've gone through all the elements in the initial array that was being passed in there. And so now my function's done. And I have to return now my final string, right? My final string in this case is just going to be the string ABC. Okay, so conceptually, it's almost identical to the previous example we saw. The only main tricky part in this problem is just that now, and kind of to what Martha was getting at earlier, now we care about what the return value is because I need to do something with that return value, right? In the last example, all I did was console log it out. Here, I care about the return value because on line 6 there, I need to add the return value to, in this case, my final string variable. So I need to know what that is. And so at every juncture, I should be very clear about why am I doing this, and more importantly, like when am I returning it, or what am I returning back to whoever called me. Okay, and just like the previous example here, notice how also this is, I guess, nesting agnostic, if you want to call it, or nesting resistant, right? It doesn't matter how many layers of nesting we have here. It doesn't matter because this recursive function is designed to say, well, I'm just going to keep going one level deeper, one level deeper, one level deeper until theoretically at some point I have to reach kind of the final depth. So I don't need a for loop. I can just have recursion do this over and over and over again until it finishes up. Any questions here? Cool. This is pretty much it for today, right? This is, like I said, like a lot of it may seem simple, but the difference between today's problems and yesterday's problems is that we no longer have the crutch of for loops to use when we kind of get in a bind here. Right now, we kind of need to use recursion. One thing to know that recursion is an idea, right? It's an idea, and so it by no means to say is something that can only work with arrays, right? We can use recursion on almost any data type, and here we just want to walk through an example where we can also do it with nested objects as well. Except obviously with objects we can't use the for loop anymore because there's no order, right? In object, so we go back to our handy function, the for loop or the handy tool, the for loop, right? And so here, if I give you an object in which every key is something and every value is a number, I want to add up all the values. Well, if there was no nesting, it would look something like this. On line 4, we start at sum equals 0. On line 5, we iterate through the object. On line 6, we have the value, which is the value. And then on line 7, we add that value to the sum. And we do that over and over again for every single value in OBJ. And at the end of it, on line 9, we return the sum. Okay, so that's kind of a very quick and dirty, simple way to add up all the values in an object if there was no nesting. But if there is nesting, well, now we see, once again, something that looks very similar into the previous set of problems. Right here, so here, if you look on line 14 there, we have a really disgusting nested object. And we look at if you look at our recursive function, right, this actually looks very eerily similar to what we did for the final string, right? The only difference here is now instead of final string being a string, it's now a sum, right? It starts at 0. Rather than using a for loop to iterate through the array, we're now using a for in loop to iterate through the object. On line 4, we're still getting the value for every key in the object. On line 5, we check to see the value is an object, and here we're basically assuming every value is either going to be a number or an object, right? There's no strings or arrays or whatever else that you want there, so we're making that kind of assumption here. And on line 6, once again, right, or even on line 8, right, if it's not an object, we just add value to the sum. If it is an object, then we recursively call ourselves, and we call some vals, and we pass in the object, or in this case a value, into some vals, and whatever that returns, we then add that to our existing sum. And so if I just kind of really quickly go through this example now, if I have my initial, as I go through the A key, for example, assume we go through the A key first, I add the value of A, which is 1, to my sum, and then I add the value of whatever that nested object is, which is for the B key. So then that requires us to call some vals on that inner object, and then so then in that iteration, the sum starts at 0, and then it says, well, your value is an object too. So then we need to remove one layer of nesting and go one level deeper, right? Almost like Inception. We go through and then we peel off the C key. So now we're looking at the D key for some vals, and once again, same idea. What's the value of D? The value of D is another object. So let's call some vals again. And notice how here we have our call stack is 4 functions deep, right? We can't finish the first function because it's depending on the second level of the call stack, which can't finish because it depends on the third level of the call stack, and then finally it depends on the fourth level of the call stack. So at every single iteration, it's waiting on something, right? It can't finish right away. Finally, on line 5, sorry, on row 4 there, we now see we're trying to get the sum vals of this object. We start our sum equals 0. The first value we get is 2, so we add that to our total. The second value we get is 3, so we add that to our total, and now we get 5. And now we can actually go back and replace whoever calls some vals with a number, right? So now we can say, great, I'm gonna return a 5. So whoever called me, you get a 5 back. And then once we get the 5 back, we'll add it to the pre-existing sum, which is 0. So now that returns 5. And then whoever called that, we return 5 there as well. And then finally, we return 5 to where that was called as well. And then our final return value is just 1 plus or equal 5, which gives you 6. And finally, we return a 6. So very, very similar in structure to the arrays. Don't think of recursion as like an array tool. Think of it as like a concept or a principle, right? It's saying, hey, I'm going to have a function that's going to do this one small problem over and over and over and over again. And if I do it enough times, I can solve a much bigger, much more complex problem, even in cases where I don't know beforehand kind of how many times I need to do something. And really, that's kind of the power of recursion, is that like you don't need to know in advance how many times you need to do something. You're basically telling recursion, hey, keep doing this until the base case is met. And that's pretty much it. So any questions? Yeah.
Hi, yes. On the previous slide, when you are or actually you're basically adding some of the value here.
Yep.
If you had, for example, if one of the values was a string, would it simply just say not a number and stop functioning, or would it add that, concatenate that string?
It will concatenate that string. It'll be a little bit tricky to see when the string hits, right? Because if you remember, if I add a string to a number, it becomes a string. Like it converts both things to a string first and then concatenates them. So in this case, if the 1 is a string, then basically everything after that is going to be added together as a string. If the 1 and the 2 are numbers, but the 3 is a string, because the 3 is added last, we'll actually add the 1 and 2 as numbers. Or actually, we'll add the 2 and 3 as a string, and then we'll add it to the 1. So it's a little bit tricky, and it depends on the order in which you do things. But you are correct in that, like, once we hit the value, we hit a value that is a string, then it will convert that to a string. It will convert the existing number to a string from that point forward, and then everything else that gets added to it will be a string as well.
Oh, okay.
Yep.
Quick question.
Yep.
In line number 7, if we have a condition else if, and we check if the value is equal to a number, then this will work for anything, right?
Yeah. If that only worked for it was a number, then we're basically saying either you're a number or an object, and if you're neither of those things, then we're just going to ignore you, pretty much. So in that case, then yes, we will be resistant to having kind of booleans or numbers, or sorry, booleans or strings or other data types in our objects. Cool. Any other questions?
Yesterday, Alec mentioned that a console log is also a function, but it does not get added to the call stack.
Yep.
Not sure why. Is there a reason why?
Oh, it is added to our call stack. We just don't see it. At least not in the way that we like, in that way that we when we print it out. A console log is like, really, if you want to kind of really split hairs on things, right? Like, a lot of things are functions here that we just kind of ignore. Like, even something as simple as a comparison, right? Like, that's a process that happens. And so if I was a computer, like, I would need to, for example, like on line 5 there, right? If I do type of value equals objects, there's two things I'm doing, or actually there's many things I'm doing that, right? The first thing I'm doing is I'm getting type of value, right? Like, that's a kind of like a function call, right? It's a process I need to run, and nothing else can run after I finish that one, right? So that's the first thing I'm doing. The second thing I'm doing is this: once I get type of value, I'm then comparing it to the string object, right? And so that's another kind of function or another process I need to do. And then the third thing I need to do is say, hey, is that true or not, right? That's what the point of the if conditional is. And so when we kind of make our call stack, when we print out these things for you, like, we want you to focus on like kind of like the core function calls. And by function calls, we're usually talking about the functions that you're writing and that you're testing. But underneath the hood, everything that we're doing here, a computer, if I was to actually look at a computer's like memory or whatever it is, like, these things are all happening very sequentially. So we just don't see it here, but they are absolutely happening in the same way that you would expect any other function call to be happening.
Okay, so on that thread is that was a pun intended. On that thread is that also considered something called enumerable objects? True?
No.
Okay.
Yeah. No, those things aren't really related.
Sorry,
Yeah, those things they're not
Okay,
they're not directly related. Yeah. Cool. Any other questions? Otherwise, we'll get you guys all started on your workshop. All right, last chance for questions.